And super resolution tries to give you a better image by applying an algorithm, which means it is the attempt to get a higher resolved image by applying a smart algorithm. So it's something like upsampling, just smarter.
Welcome to another episode of the Mapscaping podcast. My name is Daniel and this is a podcast for the geospatial community. My guest on the show today is Dr. Markus Müller. He is the lead data science engineer at a company called UP42. UP42 have actually been on the podcast before. If you go back to episode 32, you will see an episode called A Marketplace for Geospatial Data and Workflows, and this goes into a lot more depth of the idea behind the company and what you can do on their platform. But for the context of this episode, it's really important to understand that Markus and his team develop a whole bunch of interesting algorithms that can be used on the UP42 platform, and the one that we're going to be talking about today is called super resolution. So this is a really intelligent way of upsampling images, but I will let Markus tell you a lot more about it in just a second. Just a quick personal note from me. I just want to say it was really wonderful to come back from a quick break over Easter, open up my inbox and see so many emails from you. I think in a world trending shallow, in a world where there is so much competition for your attention, it's really humbling that so many of you would take the time to write to me, take the time to share your feedback, give me encouragement and let me know that you're enjoying the podcast. I want you all to know it's much appreciated. I started this podcast for some rather selfish reasons. So at the start, I thought I would be making a podcast for people like me. But over the last few weeks and months, after hearing from so many of you, getting to hear your stories, what you're working on, where you're going with your careers, I'm forced to realize that people like me is far too narrow of a definition. And I now understand that I'm making this podcast for people like us. So this might be a very small, but I think extremely important distinction. So I'm on the lookout for people like us that might enjoy a podcast like this. If you could help me out with that, I would really appreciate it. Hi Markus, welcome to the podcast. Today we've got a bit of a technical topic today. We're going to be talking about super resolution. But I think before we get started on that, could you let us know how you got involved in geospatial Earth observation?
Hi, Daniel. Great to be here. Earth observation and remote sensing. So I'll try to cut the stories short. I studied geography, of course, and I learned the basics of remote sensing at university. But then, like, my first job didn't have much connection with that. But many years later, that's now about 12 or 13 years ago, I worked in Indonesia in the context of development work. So I went to Borneo in a pretty remote place and gave trainings on GIS, and it was in the context of carbon accounting activities. So there was also a component of remote sensing. And I could just get into it. I was always interested in it. And now I had the opportunity to learn more about it. So we worked with Landsat data, rapid eye data, did forest classification, carbon accounting, and I gave trainings on the topic. Yeah, so that was the starting point, and I'm continuing on that activity since then.
I mentioned this right at the start, is we're going to be talking about super resolution. Could you explain to me and the listeners what super resolution is?
Yeah, so super resolution, that's a thing that's coming out of the computer vision domain. And the idea is essentially, so you got an image, right? And the sharpness and the quality of an image is defined by its resolution. And super resolution tries to give you a better image by applying an algorithm, which means it is the attempt to get a higher resolved image by applying a smart algorithm. So it's something like upsampling, just smarter. And the whole thing is done basically for two reasons. First of all, these images become more visually pleasing, which also means that people can identify objects better in these images. And the same is true to some degree for algorithms which are looking for objects. Research literature tells us that object detection algorithms can do better when they process super resolved images.
So we've got almost two different customers here. It feels like we do this to create more visually pleasing images, as you described it, for humans. And then we can also use them in algorithms to detect objects. Is there a direct relationship between things that are pleasing to humans, like images that we can more intuitively understand and images that are really good for machine learning algorithms?
So there is a strong connection. If you work with computer vision algorithms and what's currently going on or the last 5 to 10 years in the context of deep learning, so these modern computer vision algorithms are implemented using deep learning, or to be more precise, ConvNets, convolutional neural networks. And these are, to some degree, use the same principles as the human visual system. So what I'm trying to say here is that what a human can perceive in image and these modern algorithms can do is by now pretty similar. Just to extend a little bit more on that, if you try to develop a deep learning algorithm nowadays and you want to know that it performs well enough, the baseline that you compare your model is usually what a human can do, because humans are pretty good at interpreting images. If you can get past that, then you really got an excellent algorithm. But for now, where we are, the human cognition system is still the reference.
So I know from a previous conversation, you broke this down, super resolution, down into sort of 3 different types of super resolution. You talked about single image super resolution, multiple image super resolution, and multi-bands super resolution. But would you mind just walking us through those 3 different kinds of super resolution?
So let's start with single image super resolution. That's something that my team developed in the last year. So here the idea is you take an image, you find a smart way to upsample it, and from that one image that you get a sharper version. So currently how this is done in the context of deep learning is that you train a neural network with image pairs consisting of low resolution images and high resolution images. Then the neural network figures out how to do this smart upsampling. So that's the single image super resolution case. The multiple image super resolution case is, quite obviously you take not one, but more than one image. You can also do that in the context of video enhancement and so on. But anyways, so if you have more than one image, and they are always slightly different, right, in regard to the angle that they were recorded and so on. So out of these differences in the images, you can basically come to a higher resolved image. That's a general idea. There are a few disadvantages that I can talk about maybe later. So that's the general idea of multiple image super resolution. And the last, with what you're referring to, multi-band, the terminology it's not so clearly defined, but we both understand the same thing. So that's basically similar to pan sharpening. So I assume most of the people listening to this are familiar with pan sharpening. So the idea is that you have a satellite image that has bands in different resolutions. Like many sensors, for example, do have an RGB, a near infrared band, but also a panchromatic band. And by using this panchromatic band, which has a higher spatial resolution, you can upsample, you can inform the upsampling process of the lower resolved bands to get a higher resolution version. And that's what you can also do with a super resolution algorithm. So what we implemented also is super resolution algorithm for Sentinel-2 images. So Sentinel-2 image has images, has bands in 2 resolutions, 10 meter, 20 meter, 60 meter. And using the super resolution algorithm, you can resample all of these bands to end up with all of the bands being a 10-meter resolution. So it was one of the very first algorithms that we implemented. And to be honest here, we did not develop the algorithm ourselves, but we used something which was already published and open source.
I just want to make sure I understand the difference between pan sharpening and super resolution here in terms of multiple bands. It sounds like we have the panchromatic band and we upsample everything else, based on different algorithms depending on what we're doing, up to that resolution of the panchromatic band. Is that the limit for pan sharpening? And can super resolution, in theory, go beyond what is possible with pan sharpening in terms of the end result, the resolution of the resulting image?
Exactly, and here it's getting a little bit complicated. So that's a little bit confusing, but I'll try to break it down. Now let's take the case of pan sharpening. Let's start with that. So we are pan sharpening a spot image, which has panchromatic band, which is 4 times the resolution than the other bands. So pan sharpening just applies the same resolution of the panchromatic band. so that all of the bands in the end have the same and higher resolution. And that's the limit, right? Because the panchromatic band informs that upsample. Now, you can do the same with a super resolution algorithm. But for example, for a spot image, you would probably, I'm not quite sure if there is much worth to it. But for example, in the Sentinel-2 case, there is worth to it because it's pretty difficult to upsample that many bands to the same resolution. And Sentinel-2 images also don't have a panchromatic band. So that's the thing. So with pan sharpening, you can only go to the same resolution as the highest resolved bands that you're having. You can also do that with a super resolution algorithm with the hope that it would do better than a classic pan sharpening. Now, you can also go with a super resolution algorithm to an even higher resolution. That's the idea of single image or multiple image super resolution. For example, in the example that we were working on, we worked with a Pleiad imagery, which is after pan sharpening at 50 centimeter resolution. And after we applied our super resolution algorithm, you end up with a resolution of 12.5 centimeters. So it's 4 times the resolution of the original image.
Wow, that's amazing. I mean, this sounds so much cheaper than launching a new satellite into the sky and trying to collect imagery at 4 times the resolution of what we could have done previously. So this makes perfect sense to me. Does this mean that I could take a super resolution algorithm and apply it to the Landsat archive, the Sentinel archive, for example, and assume that I can increase the resolution, improve the imagery from the archive?
Before I answer that, I just want to make sure that we are realistic here. So the super resolution algorithms result in a better resolved image by an algorithm. So it looks better, objects are sharper and so on, but it's in quality never comparable with an image which was recorded at a higher GSD. I think we need to stay realistic, If an image is really recorded at 0.5 meter resolution, it will always be sharper. You will always find more detail than an image that was upsampled from 2 meter, for example. But coming back to your question, yes, you could do that. So one of the underlying assumptions of all of these super resolution algorithms is that they are scale independent. And what I mean with that is you develop, for example, an algorithm which upsamples 2 meter to 0.5 meter. And you assume that the same upsampling also works if you go from 0.5 meter to 12.5 centimeter. Or if you go from, I don't know, an old Landsat image with 60 meter resolution to 15 meter. So yes, you could do that. In hindsight, you could basically take these archives and upsample that. But as I'm saying, it can never be at the same quality than if you would have an image with a higher GSD.
I really appreciate you pointing that out and highlighting that because I think it's really important that this is not just the magic cure for everything. So thank you for that. When I was at university learning about remote sensing, Earth observation, ground truthing was a big part of what we did. So we would look at some satellite imagery, we would create a signature, and we would do some testing. Like, can I detect all the forest cover? Can I detect a certain kind of plant cover? Can I detect water? That kind of thing. But then a part of the job was to also go out and do the ground truthing. Like, okay, my algorithm, my analysis said there was forest of a certain kind here. And go out and you'd check. How do you ground truth the results of something like super resolution?
As you said, when we went to university, the idea of ground truth was you wanted to really know if out there in reality your model or your analysis reflects what's happening there. So, part of your project or your thesis was that you went out, you flew there maybe and had a look at what's happening on the ground and you examined it and you came up with some accuracy and stuff like that. That's not what's done anymore in the modern world of deep learning and computer vision, right? So if we nowadays look at accuracy values and so on, you compare it with other data sets. And most of the time, humans create these data sets by looking at the images, which, by the way, goes back to what I said earlier, that the human visual system and what humans can do still is like kind of the reference for what is achievable. Like a disclaimer, what is currently meant with ground truth. Now, with the ground truth, that's often problematic because very rarely you would have a real image at a higher resolution that you are going for. So you need to be smart with your ground truthing. The classical approach in computer vision, where most of these algorithms are coming from, is you create an image, you downsample an image to a lower resolution, then you apply your super resolution algorithm to it, and then you compare it to your original image. So, here again, the scale independence comes into place. And you're just saying, okay, I go back even more in resolution, sample it up again, and then I can compare it using some metrics if the image restoration process, how good it is.
Is there not like a danger that the algorithm just figures out how to reverse engineer that downsampling?
Yeah, with this opinion, I probably don't get very popular in the computer vision research domain, but I believe that many of these papers which are following this approach and creating even their training data sets with this approach, that their neural networks just figure out how to invert their downsampling method, which most of the time is cubic resampling or bicubic resampling or something along that line. So I believe if you're only doing that also for training algorithm, like, you apply a straightforward mathematical operation to downsample it, the neural network will just figure out how to invert this function. So yes, there is this danger. That's why when we did our super resolution algorithm, we did something different. Like in the Pleiad case that I talked before, the Pleiad single image super resolution. So what we did is we did not downsample and upsample, but we took the images at the original resolution at 2 meter. Then we pan sharpened them. So we also cut the same images at 50 centimeter resolution. And then we trained the algorithm with these pairs. And the nature of this mechanism is that you don't apply a straightforward mathematical operation on all of your pixels, but you have a genuine upsampling, right? And if then your algorithm figures out how to do that, it kind of learns out of the context how to create higher resolution image. Or that's at least the hypothesizing around the model.
Just so I understand this, so you had a high resolution image that you created through this pan sharpening process, and you said, okay, this is the result that we want. And then you took your super resolution algorithm and applied it to the images before they were pan sharpened and say, okay, well, this is what we have and this is what we want. Please figure out how to make the connection between those two. Is that what happened?
Exactly. And then you can also apply your metrics again. It's very important to not only visually interpret your results, but apply some quality metrics, which indicate if you really get to something better than just upsampling. But yeah, that's the general idea. But then the application of the algorithm is about going one scale higher, right? So we trained the algorithm with image pairs of 2 meter and 50 centimeter resolution. But then in the application, we apply it on images of already pan-sharpened images of 50 centimeter resolution, and we end up with a 12.5 centimeter resolution. So the combination of pan-sharpening with the super resolution algorithm, that's what makes it so powerful.
Just so I understand this, the goal of super resolution is always to go beyond what you could achieve with pan sharpening. So you test it against the pan sharpened image, and then you extrapolate out from that and say, well, we would like to increase the resolution by 4 times again. Is that correct?
Yes, exactly. Pan sharpening is a well-proven method, works great. So if you want to do super resolution based on deep learning, it's computationally so much more expensive. You need to do better than just pan sharpening to have a good reason for doing it anyway.
So for me, this kind of opens the door to using other data sources. So taking a 25 centimeter satellite image and then using perhaps Sentinel and then saying, well, this is the result, but this is the stack that I have. Please figure out how to make a connection between the two. Does that sound like a feasible way of testing this? So let's say I had a really high resolution satellite imagery, optical imagery of a certain area at 25 centimeters, and I went and took a stack of images or a single image from a different sensor, but over the same geographic area. Could I say then, okay, well, this is the result, this extremely high resolution image, and my coarser resolution image is what I have. Algorithm, can you please figure out how I can get my coarse resolution over to the high resolution?
Yes, you could do that. That would be kind of the ideal case. Now, I need to say, I don't know. I think there are almost no studies there which are doing that. And I guess the problem is that very few people have these image pairs because they not only need to be from the same area, they also need to be taken from exactly or almost the same time. So there are almost no training data sets for doing something like that. But in theory, that would be the perfect case.
A wee while ago, I was talking to the president of ISI. So this is a SAR satellite company, and he was saying one of the magical things about SAR data is that, obviously it looks through cloud. It doesn't care if it's day or night because it's an active sensor. But he was saying this really opens the door for a lot of different things because you can guarantee that you can take an image at exactly the same angle using exactly the same sensor over exactly the same geographic area. Am I able to apply super resolution algorithms to SAR data?
In theory, yes, the algorithms can be applied to SAR data as well. I got to admit, I haven't read any papers so far which are doing something like that. I need to guess here a little bit. The nature of speckle might pose a few problems there, but I would still go for, yeah, theoretically, yes, you could do that.
Because that seems to me like that would be really interesting because you'd have this really high repeatability. I know that I can take this image at this place. And then I wonder if you could use that to match with another sensor that perhaps from time to time passed over the same area.
Yeah, probably it would be smarter to do something more along the line of data fusion for such a use case. Like in data fusion, you're trying to combine the best of two or more sensors. So in your case, what you're describing, so you have a sensor with maybe only two bands, or in that case, polarizations or one, I'm not quite sure, but a very high temporal resolution. And you might try to combine it with another sensor, which has a better spectral resolution, more bands, and so on. And you can try to develop an algorithm which fuses these two algorithms. So in the end, you would have a very a high revisit, but also a lot of information in your data set.
Yeah, I really appreciate the clarification there. When we think about super resolution in general, are there any sort of standout use cases for this? Or is it just a case of the same use case that we might see if we had access to higher resolution data in general?
The major use cases, it's not exactly the same because the super resolution algorithms were good for some things and not so well for others. So I would say there are two major use cases, and we already briefly touched them before. One is simply creating sharper images for the visual observer. Even in the modern age of artificial intelligence, there are still a lot of people, too many people, interpreting satellite images and aerial imagery like manually. There are these analysts, especially I think at intelligence agencies. They have like teams of people who are interpreting satellite and aerial images, looking for specific objects. So a super resolution algorithm or super resolved image can help because it helps the human to better identify and find objects. That's number one. And number two is essentially the same, just for an algorithm. So these computer vision algorithms, which try to detect objects, they are mostly picking up on the shape of these objects, to some degree also intensity and texture, but object detection algorithms, they look at the shape. And if an algorithm is able to create like a clearer shape of an object, it makes work for these algorithms easier. And there are studies about it, so that's kind of a proven fact by now. There are also one or two studies which point out that super resolution might also help with classification problems, or as we say in the computer vision domain, segmentation problems. But there's not too much work done on that so far, at least as I'm aware.
So it sounds like a lot of these use cases, they are not necessarily dependent on the Earth observation space. Can I assume that a lot of these could be applied to lots of different kinds of computer vision in general?
Yeah, absolutely. The way it developed over the last few years is that deep neural network and ConvNets, or especially ConvNets, like the first breakthroughs in deep learning were coming from computer vision and ConvNets. There are these competitions where researchers try to find cats in images. I think by now everybody knows that. I don't know the exact time anymore, but around 10 or 12 years ago or so, suddenly these competitions were always won by deep learning algorithms. So that's where it all started. And then it took a while until the Earth observation community picked up those algorithms. And at the beginning, that was a kind of a funny time. In the beginning, we applied them, or many people in the Earth observation domain wanted to apply them, but these algorithms were tied to 3-band natural images, which also have a lower bit depth than what we are used to in remote sensing. So quite often what you could see is that people threw away all of the other bands, just took the RGB images, downsampled it to 8-bit so that these algorithms worked and applied it. So that was a starting point of the love affair between computer vision and remote sensing. Over time, Earth observation developed its own scientific research around applying deep learning algorithms to remote sensing problems. So by now, the new algorithmic developments are still coming out of the computer vision domain, but there's also a significant development in the Earth observation domain where these algorithms apply to problems which are specific to our problem, like, for example, multi-band images, SAR imagery, and so on and so on.
That's really interesting that computer vision was driving the whole thing, right? Driving the development of these algorithms. If we were to sort of visualize this, could we imagine that the algorithm or the development forking now, where we have computer vision going one way and Earth observation going another way?
Not really. It's more the other way around. It's a convergence. Like if you nowadays go to the big computer vision conferences, there most of the time is quite often there's a track for Earth observation. So, the people who are working on Earth observation problems also going on these conferences and talking about what they're doing. And Earth observation is more and more accepted as one of the application domains. Like, for example, medical imaging, which is already for quite a while integrated. So basically, there's like this core technology, computer vision based on deep learning, and there are a number of application domains. And Earth observation by now is established as being one of the application domains of these things. Communities are actually growing together. Like when we published our super resolution paper, we did the same thing that most computer vision people are nowadays doing. So we published a preprint on archive. So basically we followed the rules of the computer vision domain.
So I'm looking at your title here, and your title is Lead Data Science Engineer. When was the last time that you had a title that had something to do with Earth observation remote sensing?
I'm not quite sure if I ever had.
That's really interesting because you have this sort of deep background in it. You have a PhD in it, and you're working with the data. You're working in the Earth observation space, but you have a much more general title.
That's right. So let me think back. So when I was working in Indonesia, my title was simply development advisor, right? Because everybody was a development advisor. And then after I went to New Zealand and I worked there for land care research, my title was environmental informatics specialist. But we had some remote sensing specialists there as well. So the title was still available. But then that was the time that data science started. And in data science, it's like a technical convergence. The tools which are nowadays used by people like, my team and myself are essentially the same tools that are used at Facebook for doing recommendation systems and so on. So this is some good developments in it. You can basically switch now between these different domains with relative ease. There's a strong community developing all of these tools. I mean, nowadays with Python and TensorFlow and scikit-learn, that's all super awesome. On the downside, everybody's a data scientist, There are very few remote sensing specialists officially between us, I think.
Yeah, it's interesting that the convergence. I wonder if it's going to diverge again, where people want to sort of specify or really highlight that, hey, I am an expert in this domain, because it seems to me that the job of the jack of all trades, I mean, it's getting more and more difficult to find a job as a jack of all trades. People are more interested in specialists.
Yeah, I wonder the same, and I can't really say. So data science is still a young discipline, and with this more generic title that many things are, summarized, I guess this was a starting point. And in some regard, you are already seeing specializations. Like in data science, we are now talking about data scientists per se. There are machine learning engineers, there are deep learning engineers. There are already like subtitles developing. Now the question, and that's kind of what you're mentioning, is will we also have specializations in the domains again? Like will there people who call themselves medical data scientists and Earth observation data scientists? Some people do that, but I have the feeling right now it's more on a personal level. If you look for a job description, what I see is mostly it's saying data scientists. And then you need to read closer what domain this is all about.
So where are we in terms of super resolution if we think about the hype cycle, for example? Yeah, are we at that stage where this is still an experiment? Are we at the stage where this is a really useful tool? Are we at the stage where we can apply this at scale?
Apply at scale, yes. Useful, yes. But there's also a little bit of hype around it. I think it's a little bit of both, and I guess that's normal in business. So some of the announcements, when I read them from time to time, I have to say a little bit, there's a little bit of over-promising, but the research literature already has shown us that there's value in super resolution. Like if there is value in it for a particular problem, you need to decide on a case-by-case basis. I believe, like from the two algorithms that we developed at UP42 and which are accessible on the platform, I strongly believe that the Sentinel-2 super resolution algorithm has value in it because I would immediately use it myself. You want to do an analysis, you got a Sentinel-2 image, it is different resolution, that sucks. You just upsample it in a smart way and then you can process it. That's great. I think there's no arguing about it. When it comes to the super resolution of Pleiad images, I'm more careful because the upsampling might help your algorithm identify objects, but it comes at a cost of a higher amount of data. You have more pixels. That also means you need more processing power to analyze these images. And that's one of the limiting factors of deep learning nowadays, and that's the processing power and simply the cost. So if you take an image and you upsample it with our super resolution algorithm, you end up with 16 times the amount of pixels, which also means you need to invest 16 times the amount of compute power if you want to develop your model. So everybody, if you develop a new model, you need to see for yourself if the advantages are worth the additional cost.
I'm really pleased that you pointed that out because that's incredibly interesting. So at some stage, we've got to decide, like, is this worth it? Is the compute worth the results? Or should we perhaps just go out and collect more images as opposed to upsampling the ones we have?
Yeah, exactly. And it's hard to predict where the journey is going. I have the feeling nowadays every second week there is a new startup announcing that they will fly some satellites pretty soon. So we have more and more data available. So yeah, we will see. As said before, I believe there are some use cases where super resolution clearly can help us. But how powerful and how much we will use it in the future, we will have to see how things develop. It's also hard to predict what the algorithms will do in the future. The developments in the artificial intelligence community over the last 5 years are amazing. So who knows what we will have in 5 years' time.
Do you think Moore's law is still true today? Because if it is, it sounds like it's just a question of time before upsampling would have the edge over collecting more images, in a lot of ways anyway.
Yeah, that's a tough one. So it kind of applies, but the algorithms are also getting more and more hungry. So the neural networks over the last years became deeper and deeper. It's very hard to predict. Daniel, very hard. And I could now start trying to predict where deep learning will be going. Right now, we're talking a lot about non-supervised or semi-supervised learning, which would bring in a whole new era for deep learning, and then things might totally change. I think it's next to impossible right now to really predict where the journey will be going. And also, I don't have an answer to your question, I believe.
No, that's fine. It wasn't my intention to sort of put you on the hook either like that. When I ask questions like that, all this amazing stuff comes out of it. For example, I'd never considered that if we upsample by such a, dramatic amount when we use super resolution, we've got a compute problem. Now we've got 16 times more pixels. And I'd never thought about that the algorithm, it's not just the data, the input data that's increasing in size, but the algorithms, I think you said, are getting more hungry as well. So, that uses more compute as well. And I think that would be interesting to run some tests and sort of figure out, when does it make sense to use this, and when would it effectively make sense to launch another satellite and with a different sensor, a high resolution sensor.
We're getting quite often a question like, how does the output of the super resolution algorithm, what effect does it have on object detection algorithm? Quite often people come and do you have some metrics for us for this and that application? And my answer also is, well, if I would work in a research organization, I would probably do that research right away because I find it very interesting. I'm not, UP42 is a commercial company. We don't really have the time to do that research as well. But I totally agree. It would be interesting to look deeper into the actual value when applying these algorithms to real world use cases, like, how much does ship detection improve? Is it worth it? And questions like that.
When you think about like the future of super resolution, are you excited about it? Can you see this as being a really interesting field to continue working in it? Or will it just be a sort of a side project in terms of the bigger field of data science, Earth observation?
Yes, I believe the second. It will be a side project. So when you're following literature, but also announcement, like the real exciting applications of super resolutions are, for example, when upsampling movies. If you have a movie which is not very well resolved, and then you apply an algorithm on it, and it's much sharper. There is no discussion about it. That's cool, and people will like that. In the context of Earth observation, I'm not so sure. Coming back to the original discussion about different types, so this thing with Sentinel-2 pan sharpening, super resolution, I already said it several times, that has value, and there will be surely algorithmic improvements, but that's it. When it comes to multi-image super resolution, there are some problems. If you have multiple images, they are usually not taken at the same time. Now, if you're resolving several images not taken at the exact same time, it means that moving objects will be basically, the algorithm will more or less get rid of them. Like you have a car, and after the super resolution, it won't be visible anymore in your image. If you want to do object detection, like car detection, and the cars are gone, there's not much value in it, right? So I believe there is some value in the Earth observation domain, but it's not like a huge topic for the future, not like other topics will be.
Could you give me an idea of what some of those other topics might be when you think about really big topics, Earth observation, remote sensing?
Fusion of data sets is, I think, the big thing to come. The algorithms that you're having right now are pretty good at detecting objects. They will get better, but that works pretty well. Segmentation is also already working pretty good. What we called in the remote sensing land cover classification. If you apply these segmentation algorithms and you have good training data, you get pretty good results. But overall, I believe the exciting applications will be in data fusion. Like, how do you combine SAR with optical imagery? How do you combine imagery with other data sources like Twitter feeds and all of these other data coming out of social media or out of tracking telecommunication devices and so on and so on. And I believe that will be the exciting thing for the next future.
Marcus, I really want to thank you for your time. Thank you for your patience walking me and, of course, the listeners through this topic. You've done an absolutely brilliant job. I really, really appreciate it. Where can we go if we want to learn more? I know that you work at UP42. I will include a link in the show notes to that. You mentioned a paper that you'd published on this topic. I will get that link from you and I will include that in the show notes as well. Is there anywhere else you'd like to direct the listeners if they want to learn more?
So first of all, I think I would like to say that if you want to try out, if one of the listeners want to try out one of these algorithms that we implemented, you can access them on UP42 for free. You have to sign up and you get some free credits and you can try them out. I think that's pretty cool. If you're interested in the scientific side of super resolution, then Archive is apparently the place to go. Archive, all the preprints of all the computer vision papers are published. So you can go there, search with super resolution satellite images, and you will basically see everything which is right now going on. I think that's always a good point if you want to dig deeper.
Thanks again, Marcus. I really appreciate your time. So I really hope you enjoyed that conversation with Marcus. I hope you now understand a little bit more about super resolution, perhaps even a little bit more about the origins of computer vision in Earth observation, where we are today and where we might be heading in the future. I have to say, I love talking to people like Marcus. It's so clear that he's not a hype man. He's not here to sell us anything. He's not here to convince us of anything. He's simply presenting the facts. And I'm sure he would take it as a compliment if I refer to him as a scientist all the way through. He's someone who really believes in the scientific method and scientific rigor. Just towards the end of our conversation, Marcus mentioned that UP42 offers a free trial. So if you go to up42.com/pricing, you'll see there's a free tier there that you can take advantage of. And so you can go in and play with these different algorithms that Marcus and his team are building. You can build your own, just experiment if that's something that you're interested in. I'll put a link to that in the show notes. And that's it for another episode of the Mapscaping Podcast. Thank you so much for tuning in again this week. As always, you are more than welcome to reach out to me via email at info@mapscaping.com. You can find me on social media. I'm most active on Twitter and LinkedIn. Any questions, comments, suggestions you might have regarding the podcast, I would love to hear them. That's it for me. I hope that you'll take the time to tune in again next week. Talk then. Bye.